Okay, let's real quick talk about electronegativity and then we're going to move on. This is a little bit of a review from the end of last unit. The electronegativity is the ability of an atom and a molecule to draw the electrons in a bond towards itself. Okay, fluorine, bright red over here, is the most electronegative element. Cesium is the least electronegative according to this reference, and you can see that the trend in electronegativity across the periodic table, it increases on a diagonal from bottom left to top right. So we've talked about covalent bonds, we've talked about ionic bonds. Now we're going to take covalent bonds and we're going to characterize them. We're going to characterize them as one of two types. I don't want to say types because they're still covalent bonds, but some covalent bonds we refer to as nonpolar covalent bonds. Okay, remember, polarity really is a word that means that there is a how would I describe that? Let me think of the word. That the electron density is not uniform. Okay, one side is not uniform. If you have a molecule that is polar, that means one side of the molecule, so water for example, here's water. One side of the molecule is a little bit negative, that would be the oxygen side of the molecule, and one side is a little bit positive. Altogether, it is net neutral, but because oxygen is such compared to hydrogen, is a much more electronegative element, that side of the molecule is what we call partially negative. Okay, that's what this little delta, this lowercase Greek delta means. And then partially delta plus sign means that side of the water molecule is partially positive. So kind of like a magnet, they have two poles, right? That's where polarity is coming from. Overall, again, the molecule is neutral. If we have a nonpolar covalent bond, that means that generally speaking, the electron density around that bond is either the same as in a hydrogen-hydrogen bond, right? That the tug of war between the hydrogens is the same. They both have the same amount of electronegativity, so you would expect that electron density would be uniform between the two hydrogens in that bond. Polar covalent bonds do not have a uniform electron density, right? So and I think I've used hydrogen fluoride as an example in the past, right? Fluorine, being the most electronegative element, is going to attract more of that electron density towards its side of the molecule. And so again, you can see, I know it's kind of tiny, this is lowercase delta minus on the fluorine side of the atom, lowercase delta plus on the hydrogen side. Now for sodium and fluorine together, remember what's happening here. Sodium is going to give away its one valence electron to fluorine. So it never really makes this type of bond. What in fact is happening here is that positive charge and that negative charge are attracting the nuclei in sodium fluoride. Okay, so two types of covalent bonds, polar and non-polar. And so it's a continuum. Like a lot of things in chemistry and in science, it's a continuum. All right, and this is a reference. I can't remember which textbook this is from. It's not your textbook. And depending on what reference you use, sometimes these numbers will change. There's not a hard and fast rule about when a bond becomes polar covalent versus non-polar covalent. Generally speaking, I think most references say that a non-polar, the division between non-polar and polar covalent is about a difference in electronegativity of 0.5. This one changes a little bit more. That one's not quite as, depending on where you look. Some people will say this says 2.1. Some references say 1.9. Others say 1.7. Really, these are person-made divisions. Okay, so again, the polarity of a covalent bond depends on the difference between the electronegativity values and the non-metal atoms forming the bond. So a fluorine-fluorine bond, each fluorine has a electronegativity of 4. So altogether, I mean, that difference is 0. That is a purely nonpolar covalent bond. But let's see if we can find one that we would consider a nonpolar covalent bond that isn't 0. Okay, so we want to get to something like 0.4. So here's a oh no, that's 5. Well, phosphorus and silicon, right? 2.1 minus 1.8. That has a difference in electronegativity of 1.3. I'm just taking these two numbers and finding the difference. According to this reference, 0.3 would be a nonpolar covalent bond. It wouldn't be as pure a nonpolar covalent bond because it's not 0, but we would still consider that in the nonpolar range. Okay, polar covalent bonds would be something that have a little bit higher, like hydrogen fluoride. Let's see, OH would be one, like in the hydroxide ion. OH, that's 3.5 minus 2.1, that is 1.4. That is an example of a polar covalent bond, 1.4, somewhere in here. All right. Now, we've been talking about polarity in bonds, okay? There's bond polarity, and there's molecule polarity. They're not the same thing. Obviously, polarity means the same thing, an uneven distribution of electrons or electron density. For bond polarity, that would be an uneven electron density in a bond. For molecule polarity or molecular polarity, that would be an uneven electron distribution in a molecule. So again, here is a water molecule. Kind of very similar to the one I drew a couple slides ago, right? Where you can see that the oxygen with its greater electronegativity is going to attract the electron density around itself more than the hydrogen is able to. So we've got the polarity of the bond between hydrogen and oxygen. That difference is 3.5 minus 2.1. Oh, we just did this, right? This is 1.4. But we can also see that the molecule itself is polar as well. Now, let's see. So bonds can be polar and molecules can be polar. Okay. You can't see this. I need to make this smaller. There's a question under there that says, can you have nonpolar molecules that contain only polar bonds? That's an interesting question. And the answer may be different than what you think. So let's talk about molecules and polarity in molecules and what dictates if a molecule is polar or nonpolar. Well, a polar molecule has to be asymmetrical in some way. Okay, so if we look at the water molecule, right, we can draw a line of asymmetry there. Okay, there's a line here that where if we go in geometry when you do reflections, I don't even know if they do that anymore. If we were to divide the water molecule like this, it looks symmetrical, right? But I can also divide the water molecule like this, and it's not symmetrical. I don't have hydrogens on both sides of this line. I don't have lone pairs on both sides of this line. So if I can draw a line of asymmetry, that means that my molecule is polar. Okay, if I have a molecule that is symmetrical, no matter how I slice it, whether it has polar or nonpolar bonds, if I have a molecule that's symmetrical, then that is nonpolar. So symmetrical molecules are nonpolar, asymmetrical molecules are polar. Okay. Now, if you have something like this is a carbon dioxide molecule, right? And you've done the Lewis structure. You've done the Lewis structure for this, right? It's 2 oxygens double bonded to carbon. This is a symmetrical molecule. If I cut it this way, symmetrical. If I cut it this way, symmetrical. There's not a way for me to cut this to make that I won't be able to reflect that structure over a line. Okay. All right. So that's kind of the fast and dirty way to figure out whether you have a polar or nonpolar molecules. Okay. Essentially, if you're, well, we're not going to talk about dipole moments, but this really is the simplest way to figure it out. Now, we've seen that there's water. We're not going to talk about hydrogen bondings yet. Okay. So what we have been learning about is VSEPR, valence shell electron pair repulsion theory, molecular shapes. Okay, so for VSEPR, what drives the shape of a molecule is the number of electron domains around the central atom. Okay, I don't know if you've kind of surmised that yet or not, but it's the number of electron domains around a central atom that gives a molecule its 3-dimensional shape. Okay, now what I would like you to do is, while I'm not going to be there for at least first hour, I want to go through, let me pull this up. This is what I want you to do while I am not there. Okay, I want to show you what I've left Mr. Delosier with for you to, I thought I had this already pulled up. Oh my goodness. What's happening? Honors chemistry. Where are we? Are we in desktop? We are. Is this it? Yeah. Okay. So I want to show you what I'd like you to do today. I've just kind of given you a thumbnail sketch on this. I've given you a thumbnail sketch on types of bonds, right? Polar or nonpolar covalent. How we find them is the difference in electronegativity between the 2 atoms in the bond. And then molecule polarity is their symmetry. Okay. I want you to do the first 4 pages. I'll do the first one with you to show you, and this is long. This is what we're going to be working on. I think we need practice. This is one of those things where the more we practice, the better we get. So the Lewis structure for this is methane. We're just drawing the garden variety Lewis structure, CH4. Remember, you may have to, some of these you've seen before, so you may know what they look like, but we have to figure out the number of valence electrons. Carbon has 4, each hydrogen has 1, there are 4 hydrogens, so there are 8 valence electrons altogether. Okay, so I draw the Lewis structure, and that enables me to see how many bonding groups I have on the central atom. Sometimes we call those electron domains, right? Oh no, excuse me, I misspoke. Number of bonding groups. How many bonds do you have? You have 4 bonds. How many lone pairs are on this atom? 0, right? So when I look at my little VSEPR chart from the PhET activity that you've been doing, you will see that a molecule that has 4 bonding groups and 0 lone pairs has a molecule shape of, this is called tetrahedral, and I'm talking about molecule shape now, not electron shape. It would look like this in 3 dimensions. This is where I would draw the wedges and the dashed lines. Okay, so there's my tetrahedral. It's also asking for bond angles. Well, tetrahedral bond angles are 109.5 degrees. Right? All of them, remember, this is the one where to maximize the electron repulsions, the electrons in bonds will achieve a bond angle of not 109.5, not 90, like it looks as if it would be in the Lewis structure. All right, so what types of bonds do we have here? We only have one type of bond. We have a carbon-hydrogen bond. I would go back and I would find the, I would go back, oops, I don't think where am I trying to go? Class notes right there. I would go back and find the electronegativities for both elements in the bond, by the way. Let's see, carbon is 2.5, hydrogen is 2.1. 2.5 minus 2.1 is 0.4. What kind of bond is that? That is a nonpolar covalent. Okay, I've given you the difference in electronegativity, right? Difference in electronegativity and bond type. You can use this. Now you'll notice that for this reference, the ionic is a different number, but that's okay. Just go by this. Now, molecule polarity. Right? If I looked at this molecule, you should know this. It's a little bit hard to see. If you have a tetrahedral molecule with all of the same atoms attached to it, so 4 of the same, that is a nonpolar molecule. The electron density surrounding that molecule is the same all the way around it. Okay? So we have nonpolar covalent bonds. The difference in electronegativity is 0.4. The molecule polarity is nonpolar because it is the electron density and the molecule itself is considered symmetrical. Now, what happens when you get down here to something like this? I'm not going to do the whole thing for you, but there I will actually, well, yeah, I've got some bonds here. There are 2 types of bonds. I've got a carbon-bromine, and I've got a carbon-chlorine. So you need to find the difference in electronegativity between these 2 different bonds, right? So one of them may be polar and one of them may not be, and that's okay, right? So that is what I would like you to do today. I'd like you to get through page 4. I gave you some background information that will be helpful, I hope, and good luck. Talk to you soon.